So we get back with the basic formulation of the statistical learning theory. I just wrote here the basic inequation we found. So there was a small mistake, my mistake. Like last both lectures, I used like greater than or equal. Actually, it's just greater than epsilon. There's no equal here. So just to make sure it's recorded so people can see afterwards. So I use the greater than or equal, and it's just greater than, okay. And instead of using this m, we could use something like m of n, because this is the scattering coefficient. It's a function that grows according to the sample size. But Vapnik usually, or not just Vapnik, but some papers usually refer to this function as this, as n of fn. That means like something connected to the cardinality of the space of the miscible functions or bias in terms of the sample size. That's actually the scattering coefficient, right? But it's just another notation, a different notation for the scattering coefficient, but it's the same. Just to remember again, I said that in the first lecture, all the risks must be in range 0, 1. It's impossible to deal with risks outside that range with this formulation. We can adapt it to work with a different range. It's possible, it's not difficult. If you guys are interested, you can use the Hoffedin bound on this side, and you're gonna have some sort of division here. I can show you later, maybe if you are interested. But divided by the sum of differences, and that's also possible if you wish, if it's better for you. I mean, if you have, for example, a situation where you are considering some sort of regression rather than just classification. That would be, of course, better. Okay, so on top of this, I think we could give a next step. My next step will be this. All of this formulation is for a single sample. So I have just one sample and I'm measuring the empirical risk or the risk I have in that sample and comparing that risk or that error, if you wish, if you prefer, to the expected risk or the expected error. The error for the examples, the unseen examples, the examples we've never seen before. We're going to apply our model F in that particular domain and see what happens. That's what it means, basically, right? So there is something quite important here. We can somehow define delta to be equal to 2, our scattering coefficient for a single sample, times the exponential value of -2n epsilon squared. And using that, we can isolate epsilon to find which is the ideal epsilon. That's an important step if you want to analyze a given algorithm or compare your algorithm against several others and have some sort of fair comparison in that sense. So as next step, I will apply the exponential and the log in the scattering function, the scattering coefficient, to have something like this. So I apply an exponential and a log function on this guy to have this, times the exponential of -2n epsilon squared. In that situation, I can sum up the powers of both exponentials and end up with this, the exponential of d log of n fn minus 2n epsilon squared. From that, the next step I will give, and this is delta, this is our delta, I will try to isolate epsilon, and that was something that Vapnik did, because after having that epsilon, I could use this inner part of my probability. I could apply my epsilon here and see how it's useful to understand the differences or the divergences we have in between both risks. And that's quite interesting. And that's probably the most important thing, the most important conclusion after the statistical learning theory. I mean, we could talk like a lot about the statistical learning theory, but at the end of the day, the most important thing is this last step. Because all those steps, previous steps, were just to justify somehow this last one. So as a last step, from here, I will isolate epsilon. And to isolate epsilon, of course, I will apply a log on this side. So I have log of delta equals to the log of everything. 2 times exponential of log this guy. So if I do that, what will I have? I'll have, of course, I have the log of a product, so I can use the sum of logs, right? So we will end up with something like log of delta is equal to the log of 2 plus the log of this exponential function. And of course, that will help me to take out the log function, the exponential function, sorry. Exponential function. Okay, so here I can remove this exponential function. I'm gonna cancel it out. So we have log of delta to be equal to log of 2 plus log of the scattering coefficient for a single sample minus 2 times n epsilon squared. So now we can isolate epsilon. So our epsilon will be something like this. Let's do it like step by step. So we will have like a minus log 2 minus log scattering coefficient of the scattering coefficient is equal to minus 2 n epsilon squared. And of course now we can divide by minus 2n. So we have, just to simplify, I'm going to divide all this term on this side by minus 2n. So I have epsilon squared equals to this term. So I can apply a squared root on this term. If I apply a squared root on this term to isolate epsilon here, I want you to notice that every time if I come back here, I just have the option of epsilon to be greater than 0. Could be equal, but it's impossible to be negative because this is an absolute value, this is a norm, right? So it has to be positive. So as it has to be positive, when I have assessed that squared root, I don't have to look for the negative side, just the positive side. So epsilon is equal to this, is equal to this term. So from that, that's something, probably that's the most important step. Now I can get that epsilon and apply just inside this probability. That's very important, very useful, because now I can understand how big is the difference I have from my model applied in my sample, in my training or test or whatever sample, and compare that to the empirical risk, to the expected risk, sorry, to the risk in the real world, to the risk for never seen examples, for unseen instances. So from that, I'll just clean up just this part, because now I'm gonna leave this just to remember, because now what Vapnik did was this. So I have this supremum value of f in f, and that's the worst case situation. I think you guys remember from the previous videos and also from the previous lecture, to be greater than epsilon. And that was my mistake. It was greater or equal, but it's actually greater, just greater. So from that, I could apply this epsilon on this side, on this right side, and formulate the differences we have in the worst case situation. And that's something important. And that's something, I mean, now we have somehow to remove the absolute value. The absolute value. How can we remove that absolute value? I mean, are we sure that maybe one of those risks is greater so that we can avoid the absolute value? In fact, yes, we are sure. We are sure that every time we compute some empirical risk, that risk is being computed in terms of our data set. So, of course, in the worst case scenario, is a case where I have the greatest overfit. When I overfit, this term will be probably as close as possible to 0, or as close as possible to some small value. Not necessarily 0, but as close as possible to some small value. And this will be very big. So I'm sure this term will be closer, somehow closer to 1 in that situation, this closer to 0. And if that's not the case, if I don't have like the worst case scenario, if I have some fair situation, even in that situation, as my classifier is being driven by data, that risk will always be smaller. So this empirical risk will be always smaller or eventually equal to the expected risk. So from that, I take this conclusion. I could invert this and have this expected risk minus the empirical risk of f, and this is by definition. This is by definition. So this subtraction must be greater than epsilon. And probably now you know something you already know, but it's good to remember that this is for the missing cases. What I mean by missing cases or missing situations are the situations our classifier didn't work. Because I'm computing when it didn't work, when it somehow surpassed that bound, that epsilon limit, that divergence, that bound, that threshold. So somehow, if that's the missing, I could look to the other side. I could look to the hitting cases instead, to the cases that somehow we had a good solution. So the cases we had a good solution were when this difference was not greater than, but it was somehow smaller than or equal to epsilon. So this is the hitting cases, or the cases where our classifier has indeed worked properly, whose results were good. So here we had good results according to our threshold epsilon. So in that situation, I apply this epsilon on this side to have a next step and to understand what's happening now. So that's the next situation. So now we'll have something like this. I'm going to clean up just this part. From this, Vapnik formulated what is called the generalization bound. So the generalization bound, and this is for one sample, for a single sample, because there is another bound for two samples. I'm going to talk about it next, right after. So for a single sample, it is the expected risk is less than or equal to the empirical risk plus this epsilon term. And this epsilon term, as you guys can see, it will be like 1 over